notation. Many of you are familiar with it, but let me start there anyway. So assume that I have S naught, mu naught, and S1, mu 1, two measure spaces. And assume that, so I represent here S naught with a measure mu naught, and S1 with a measure mu 1. And assume that I have a map T or a map X from S naught to S1, which is measurable. Then I am going to say that S pushes mu naught forward to mu 1, means that if I take any set B here, and I look at the pre-image, S inverse of B, then I have conservation of mass. The measure of S inverse of B with respect to mu naught will be the measure of B with respect to mu 1, and this holds for every B measurable. So I am going to be using often this notation. Here, a typical example I am going to refer to often. The first example is when S naught mu naught is the d-dimensional cube and the Lebesgue measure restricted to the d-dimensional cube. And S1 mu 1 will be RD, and any probability measure on RD. Another example which I want to mention is, let us consider the projection pi naught and pi 1 from R to D to RD, given by pi naught of xy equal to x, pi 1 of xy equal to y. And take a gamma to be a probability measure on R2D. Then when I use pi naught to push forward gamma, I call this the first marginal. Of gamma. And when I use pi 1 to push gamma, I call this the second marginals of gamma. Having this, I can define the Wasserstein distance. So let mu naught and mu 1 be two probability measure on RD. And to avoid triviality, I am going to choose P2 of RD. So this is the set of mu probability measure on RD, such that the second moment is finite. So the Wasserstein distance between mu naught and mu1 is denoted as W2 mu naught mu1, and the square of it is obtained by minimizing over the set of gamma, the integral over R2D, x minus y square, gamma dx dy, where the first projection of gamma is mu naught, and the second projection of gamma is mu1. And in short, I am going to write that gamma has mu naught and mu1 as its marginal. I am going to write it that way. So if you try to prove that W2 is a metric, mainly you want to check that it satisfies the triangle inequality. It is better to write it to use a different formulation to make your task easier. And this formulation is contained in the following proposition. So this is an elementary from measure theory. Set H to be the set of map from 0, 1 to the power D to RD, and I endow this set with the Lebesgue measure. This is a Hilbert space. And you can guess what inner product I am using. First, the map with 2S in H associate S push forward the Lebesgue measure. This map is surjective. And if this is a mu, I am going to write that the law of X is mu, in short. And the second statement, once you have the first one, is the Wasserstein distance between mu naught and mu1 is the infimum over x naught, x1 in H. You take the norm of S naught minus S1, the Hilbert norm, where you impose that the law of X naught is mu naught and the law of X1 is mu1. And clearly here, it is easier to check that what we define, what we meant to be a metric will satisfy the triangle inequality. Now, if you compare these two results, let me consider the following quotient space to be able to interpret these two results. I say that X and Y in H are equivalent. If the law of X equal to the law of Y. And I am going to write the class of equivalence of X this way. So according to what I wrote at the top, when you look at the set of probability measure with finite second moment, and you compare it to H quotiented by this equivalence relation, you have an isometry. So this is the first hint, which is going to motivate how we want to define a differential structure on the set of probability measure. So there is a differential structure which has been defined by Ambrosio, Gigli, and Savary. And I would like to rely on this isometry, which I use above, to show that the differential structure by Ambrosio, Gigli, and Savary is equivalent to the differential structure on the quotient space. So here is the gain. If you are able to express the intrinsic differential structure using the flat differential structure, here are the gain. First, differential structure. On the flat space. Are easier to understand. So to give you an example, if I take S0 and S1 in H, and I want the geodesic connecting S0 to S1, it will be given by 1 minus T S0 plus T S1. So this is one advantage to have a flatter space. And I want to argue later that the differential structure on the set of probability measure is the same as interpolating between random variables. Another gain is the study of ODEs or PDEs on the set of probability measure of finite second moment translates into studies on the flat space H. For instance, when you want to study Hamilton-Jacobi equation on the set of probability measure, a theory of Hamilton-Jacobi equation has been well developed on in Hilbert setting by Crandall and Leon. So if you can compare Hamilton-Jacobi equation on the Hilbert space with Hamilton-Jacobi equation on the set of probability measure, you will be able to get, for instance, comparison principle easily on the set of probability measure. You will be able to prove existence and uniqueness, exploiting what you know on Hilbert spaces. So let me recall a definition which most of you are familiar with, but simply I want to be sure that we agree on the same notation. Definition. I want to define what is the subdifferential I want to recall what is the stop differential of function on the Hilbert space. So let U hat be a function from H to R, and let X not be in H. We say that zeta naught in H belong to the subdifferential of U hat at S naught, and we write zeta belong to the subdifferential of U hat at S naught if U hat of X is greater than U hat of X naught. Plot zeta naught X minus S naught, the inner product on H plus little o of the norm of X minus X naught. So this inequality holds if X is close to S naught. So this is something we are very familiar with. And I am going to write something analogous on the set of probability measure. But in fact, I am going to show you that it is not very different from what I wrote here. So let us observe that zeta naught being H mean that zeta naught is a map from 0, 1 to the power d into Rd, such that the integral is less than infinity. So later, when I talk about, when I compare vector field to subdifferential on the of a function defined on the probability space, we should not be surprised that this subdifferential will be a vector field, because in the Hilbert space already, our subdifferential is a vector field. I need the following notation. If mu is a probability measure on Rd of finite second moment, when I write the gradient Cc infinity of Rd, and I close it with respect to mu, I mean simply this is the set of gradient of phi. Phi is of class C infinity of compact support in Rd. So computing the gradient, I have a vector field, and I am going to close this with respect to the Hilbert structure L2 Rd, and I am using a measure mu. So what I mean is psi is in this set is equivalent to, there exists a sequence phi n from 1 to infinity, of a compactly supported function of class C infinity, such that if I look at the integral over Rd of psi of x minus gradient phi of x square, and I integrate this with respect to mu. I compute the limit when n goes to infinity. I get 0. And so the element I am describing here are approximation of vector field which are smooth and which are gradient of function. So here is the definition due to Ambrosio, Gigli, and Savary. Let U be a function defined on the set of probability measure and taking a finite value, and let mu naught be a probability measure on RD. So I want to view the set of probability measure as a manifold. I have not told you yet why I will expect to have a manifold structure, but this is where I want to get eventually. We say that psi naught, which is an element, a vector field, of V space, belong to the subdifferential of mu naught of U at mu naught if the following hold: U of mu minus U of mu naught. The first part is what you expect, is greater than, I will need a linear term plus little o of the Wasserstein distance between mu and mu naught. But my linear term will be here, the integral over R2D of psi naught of x, y minus x, gamma ds dy. How do you choose the gamma? You are going to consider the gamma minimizing the Wasserstein distance. So you write the infimum over gamma, which has mu naught and mu as marginals, and minimizing the Wasserstein distance. So I am saying that if you compute the distance between mu and mu naught, it is the integral over R2D of x minus y square gamma ds dy. And I characterize that by gamma 0 mu naught. So 0 is to mean optimal. So it is very natural if we should minimize over the set of optimal gamma, or we should maximize over the measure of gamma. Call this relation 1. We have a following theorem, which is due to me and Tudorescu. One is equivalent to U of mu minus is greater than U of mu naught plus the supremum over gamma, having mu and nu are marginals, the integral over R2d, psi naught of x, y minus x, gamma dx dy, plus little o of W2 mu naught mu. So I am saying that in one, instead of minimizing over the set of gamma which are optimal, I can take any gamma. I want to give you an idea why this result is true. So once you understand the intuition why it is true, you can write a rigorous proof which is just a little bit more technical. So idea of the proof. So I am going to take a gamma optimal between mu naught and mu, and gamma bar optimal between mu naught and mu. And I want to compare the integral over R2d psi naught of x, y minus x, gamma ds dy. I want to see how it is comparable to the integral of psi naught of x, y minus x, gamma bar dx dy. More precisely, if I can show that this is smaller than little o of the Wasserstein distance between mu naught and mu1, mu naught and mu, I'll have proven my theorem. So instead of, I am supposed to take up psi in the closure. I am supposed to take psi in the closure of that set, but just to give the idea of the proof, assume that psi equal to the gradient of phi, where phi is of compact support of class C infinity. And once I know how to prove the result in that case by an approximation argument, I can extend the result in the general case. So let us observe that if you write phi of y minus phi of x minus gradient phi of x, y minus x, you can write this as r over 2, the L infinity norm of the second gradient of phi, y minus x square, where r is a function which is between 0 and 1. Now, I am going to write the integral over Rd phi of y mu dy minus the integral over Rd of phi of x mu naught dx. Let us observe that because gamma has mu naught and mu1 as marginal, this is phi of y minus phi of x, gamma dx dy. Because gamma bar has mu naught and mu as marginal, this is phi of y minus phi of x, gamma bar dx dy. So I am going to copy what I wrote there. I wrote that the integral over R2d of gradient of phi of x, if I combine these two identity, y minus x gamma ds dy minus the integral over R2d gradient phi of x y minus x gamma bar dx dy in absolute value is less than the integral over R2d of R, the L infinity norm of the second derivative, gamma ds dy, plus the integral over R to the 2d. The L infinity norm of the second derivative of phi, gamma bar ds dy, and this is less than 2 versus 10 distance square between mu naught and mu, and that finishes the proof. So once you have the proof in the case, this particular case, by an approximation argument, you can extend the proof to the general case. Any question? Okay. So next, I want to move to a situation where I am going to exploit the fact that I have a quotient space. Definition. This is about rearrangement invariant function. We call U hat from the Hilbert space H, which is L2, 0, 1 to the D, RD. The Lebesgue measure restricted to 0, 1 to the D into R. Rearrangement invariant if U hat of X equal to U hat of Y whenever the law of X equal to the law of Y. Just as a curiosity, this terminology was motivated by the following fact. Assume that you have S from 0, 1 to the D into 0, 1 to the D, which pushes the Lebesgue measure to Lebesgue measure. So you call this a measure preserving map, and take S in H. Then if you set Y to be X composition S, this implies that the law of Y equal to the law of X. Conversely, let X, Y in H be such that the law of X equal to the law of Y. Then you can write that y minus s, composition Sn. There is a sequence of measure preserving map such that this limit goes to 0. So when you write y equal to S composition S, you call X is a rearrangement of Y using a measure preserving map. And this is what motivates our definition. So when U is rearrangement invariant, we can define U of mu is U hat of X, where the law of X is mu. And this function is well defined because U hat depends only on the law of X. So in other words, U hat is rearrangement invariant, meaning there exists a function U such that the U hat can be written as a U composition the law of X. So we have the following theorem. This is due to Tudorescu and myself. Assume that U and U hat are as above. So by that, I mean that U hat is rearrangement invariant, and so U hat can be factored into U composition law. If zeta belongs to the subdifferential of U hat at X, is an element of minimal norm, so let me slow down here and explain what I am saying. One can show that this subdifferential is a convex set, which is closed. And so it has an element of minimal norm. If psi is in the subdifferential of U at mu is of minimal norm, then you have a factorization zeta equal to psi composition X. So this gives you a relation between the Hilbert gradient and the Wasserstein gradient. So this tells you that if you have a PDE on H, you can convert it into a PDE on the set of probability measure. So assume that I have a PDE involving a Hamiltonian H of X, gradient U of X. I can convert it into a PDE, H of mu, gradient U of mu. So I would like to make the following comments. So observe that I did not say that psi is in the sub-differential of x, imply psi can be written psi composition x. This is not in general true. It is true only if I am talking about element of minimal norm. It is also true if psi, if the function is differentiable, then the gradient is the element of minimal norm, and this is true. However, when you are studying viscosity solution, you are dealing with a function which are not differentiable. You talk about sub-differential and super-differential, and so you are not in the situation where the gradient exists. So assume I have an equation, Hamilton-Jacobi equation. Assume I am looking for solution to this equation. So if I can have H of mu psi, this will be an H hat of x psi composition x. So I will be missing general zeta. However, if I choose H to be linear, then one can show that two holds. Therefore, if I want to study Hamilton-Jacobi equation with linear Hamiltonian, I can go from the equation on the set of probability measure to an equation in Hilbert space, vice versa. But because every function, converse function, imply H is a supremum of linear function, you can conclude that you can set the theorem. Let H hat of x psi be h of mu psi, where x, the law of x, is mu, and psi composition x is the projection of zeta on what I will call gradient fx. So this means the projection on the set of vector field which can be factored into this. Then when you study the equation, has a unique solution, viscosity solution. If this is convex, plus some standard technical condition, which are the condition you need to have existence and uniqueness of viscosity solution on the Hilbert space. So to summarize, if you give me an arbitrary Hamiltonian on the set of probability measure, I will not be able to say if my Hamilton-Jacobi equation has a unique solution. If the Hamiltonian is linear in the momentum variable, I will be able to say I have a unique solution. If instead of linear, it is convex in the momentum variable, I can exploit the fact that a convex function is a supremum of a affine function to conclude that my Hamilton-Jacobi equation has a unique solution. And of course, I am not telling you what are the standard conditions on the Hilbert space, but these are well-known conditions which, when you apply them, you can solve uniquely your equation.